So let's evaluate the model. For evaluating the model, we use something called an adjusted RAND index. It's a measure of the similarity between two groups. Okay, so the goal here is we have a group of actual test data, that is the actual scores that we have. Sorry, the actual numbers that we have. So we know that each case in our data set, we know what the number is, right? We know whether it's a 1 or 2 or a 3. And we also have the predictions. That's what our model is predicting. And we want to see what's the similarity between these two sets. Are they reasonably similar? We're not looking at actual values. We're seeing whether the differentiation is similar or not. Okay, and you can look at that thing over there. So if there's 0.0, then there's no similarity at all. And that's completely random, any overlap in that. And 1.0 indicates that the two groups are identical. So let's run that. And we get 0.567 similarity. That's not so bad. We've done a very basic model, so it's not great, it's not terrible, but it's better than random, because this is 0 would be random. So we are pretty much along the way there. And again, since we have categories over here, we've got cluster numbers and all that kind of stuff. We can again draw a confusion matrix of sorts with this. So this is going to be a little bit different, the confusion matrix, but let's take a look at it and then I'll explain it. So because it's a little bit confusing here. So what this confusion matrix is doing is, we have a cluster number and actual prediction, right? So what this does is, each row in this corresponds to a number in the test sample. So each row is, so this is row 0 in the test sample, okay? And each column is the cluster assigned to that case by the model. So what this is saying is that for our actual zeros, none of them were put in cluster 0, none of them were put in cluster 1, so none of them went to cluster 0, none of them went to cluster 1, 43 were assigned to cluster 2, and none of them went to any other clusters. So if you're looking at our zeros, we've done a great job of identifying them. If we get a cluster 2, we are reasonably confident that it's a 0, or rather, if our model is, let me rephrase that, if our model is seeing a 0, then it's going to put it inside cluster 2. So that's a great number, right? Rather, it's a testing sample, it's not the training sample. Can it tell us confidently the other way? Well, almost, because if we find that we have cluster 2, then the only case in cluster 2 that's not identified as 0 is this one here, which is 0, 1, 2, 3, 4, 5, 6. In one case, it took a 6 that was actually a 6 and identified it as put it in cluster 2, which is a 0, right? So with zeros, we've done a very good job. So given a 0, we can with reasonable confidence, and cluster number 2, we can with extreme confidence actually say, hey, that's a 0. But let's look at something else. Let's look at 7, right? So that's 0, 1, 2, 3, 4, 5, 6, 7. No, not 7. Let's look at this one. So that's, all right, let's look at this one here. There's 0, 1, 2, 3, 3. Let's look at a 3, right? So the 3, this is a column, the row for 3s. So 3s get assigned to cluster 0 in one case, 1, 2, 3, cluster 3 in one case, and so on and so forth, but cluster 8 in 39 cases. So in 39 cases, we're getting a 3 in cluster 8, and in 4 plus 1, 5 plus 1, 6 plus 1, 7 cases, we're getting a 3 in some other cluster, right? So again, that means that we have a precision essentially of 39 divided by 39 plus whatever that the denominator is, right? So 4, 5, 6, 7. However, if you look at the other way around and we look at this, at the column, that is column number 8 over here, we find that in column 8, in cluster 8, 39 of them are 3s, but 1 is a 2, 16 are 5s, 11s are 8, and 40 are 9s. So if given that we get a cluster value of 8 for a figure, can we with confidence say it's a 3? Not really, right? Because we have so many cases where it could be a 9, or it could be a 8, it could be this thing. In fact, there are more 9s than there are 3s in that cluster. So that's done a very poor job of identifying the cluster correctly, right? So this is what you want to do with a confusion matrix. You want to see how well it's actually figured out the clusters themselves. So you look at this stuff and you can then decide for each digit how well it's been doing. Maybe try to get more data or more or a higher pixel rate, or higher resolution before you actually work and say, hey, maybe we get a better bet. But we can see our 56% RAND score is coming from the fact that we are doing well on some numbers. Like we're doing well on 0, we're probably doing well on 0, 1, 2, 3, 4. Yep, we're doing well on 4, because 4 we have 0, 1, 2, 3, 4, right? 50 cases that are in cluster 1 here. 50 cases in cluster 1, and only 2 plus 1, 3 plus 1, 4 cases that are, 5 cases actually, plus this that are in other clusters. And even more important, cluster 1 doesn't contain anything except 4s. So if you get a cluster 1, you can say, hey, that's a 4, right? Even though you may not recognize every 4 correctly. So that's how you sort of analyze the results of your clustering analysis by looking at this confusion matrix. Finally, what we can do is we can look at the graphical view of the cluster. It's kind of interesting. And what we'll do here is we'll run a principal component. We'll take so the idea here is that our graph is 2-dimensional because it fits on this page. Our data is n-dimensional because we have n features, right? As many features as we have. So what we can do is we can reduce our dimensions to 2 using principal component analysis. So we import this decomposition from sklearn and run PCA on that and say we want only 2 components from our training sample. And once we've done that, we can, let me draw this and show you, we get a really nice picture. It tells us these are our data points reduced to 2 dimensions, and these are the clusters where they come in here. It would be nice when we look at this if we could see the boundaries were clearer, right? So we can see that some of the boundaries are reasonably clear, right? For example, there are very few on the boundary between the orange and the blue, and the orange and the purple and the blue. But if you look at the blue, the light blue and the green, and the light blue and the brown, and the light blue and the dark blue over there, and that area is very, very messy. So what you would like to see in a good result would be the very few points at the boundaries, so that the clusters are reasonably accurate, right? So there are 10 clusters over here. So that's the goal in clustering algorithm. A very brief introduction. I suggest you read up more about it. And that pretty much ends our entire course over here. I think what we've covered in this course is the basics of Python, and really how to use Python to get data from the web, how to use Python to do some basic analysis with it, like basic visualization. And like I said, there are many, many tools out there that do a better job, so you should probably look at those. And how to do Python to do some, get understanding out of pieces of text, how to use Python to analyze graphical networks, and how to do some very simple machine learning algorithms, or how to use some very simple machine learning algorithms and do some simple tests on machine learning, and how to actually, more important, interpret the results and then work towards getting better results using these algorithms. And of course, we segued a little bit into SQL and database design. The goal there being that down the road, these things are going to help you in understanding how to deal with data better. I hope you enjoyed the class. Thank you so much.